Hello, everyone. Today's lecture is correlation analysis. Up to now, we started only with a single factor, or we studied multiple data analysis, comparing two independent sample, comparing two dependent sample. This is actually is more or less like comparing two dependent sample. The only difference is it's called for studying the correlation analysis. We study bivariate data. We have two independent paired samples. So the sample size for the first variable is exactly the same as the number of the number of observation in the second variable. So it's like a pair of observation, and this is what you need for the correlation. The definition of a correlation, it's like correlation means that um, a measurement of linear relationship between two independent variables, two pairs of data set. That's what how you define the correlation. It is first described by Carl Pearson. He is a great statistician, English statistician. This term, the correlation term, was introduced by him like in the 20th century. So it was like in our life, more than 100 years of time, the correlation. So you need a bivariate data. When we talk about a bivariate data, say X and Y, where the observations are paired. So this means that the first observation on X is paired with the first value of Y. The second on X with the second on Y, and so on. So this is this lecture note. I scanned this lecture note from the book of Introduction to Business Statistics, which is a very old book. I bought it 20 years ago when I was abroad, long time ago. But I like this book really. I mostly study this book. I teach this book in the first semesters. I like it very much. So the name of the book is Introduction to Business Statistics, a computer introduction to business, a computer integrated approach by those three guys. So you can. It is difficult probably to buy this book. They might have a better edition already, but I still like it. It is worth to teach this book anyway. This subject I found it very useful in this book, so I wanted you to have it like digitally scanned, and I didn't want to spend writing. This is much more professional, much readable for you. That's better. So this is a good example, just to clarify the idea behind the correlation analysis. Assume that um, let me have assume that a personal department has gathered sample data on the age X, annual income Y of 8 employees. So the data are you have 8 person, their age and their incomes for each in $1,000. So the person whose age is 35 has an income $37,000 a year. Um, Whereas for 50, a person whose age is 50 tends to earn $60,000 a year. So it's clearly you may observe that when the age is increasing, the income is increasing. So this is a relationship. So it's clear relationship. When it is decreasing, the income is decreasing. So the basic idea of the correlation coefficient is to tell you whether the increment is in the same direction or in the reverse direction. So this measurement is measured between -1 and -1 and +1. A zero correlation means no relationship. No matter what the age is, the income won't change. So that means there will be no correlation. So to understand the relationship, so the book has already draw a picture of this diagram, a scatter diagram. For each age, its income is drawn. For instance, this one is like 26 something. Let me see. Yes, this is the second observation. So this stands for the second observation, 26, and the income is 29. So it comes to that way. So this is the income y, and that's the age. And this one is like 31 something, and the income is 36 or 37. Let me see, 31. Yes, 31 is here. The fifth person has an age 31, and the income is 35, which is, yes, maybe, yes, that's one. 31. And this one, let's see this one. This is the person whose age is 50, and remember that he's earning $60,000 a year. That's how you bring this scatter plot. So it's clearly that will tell you that as the age is increasing, and the income is also increasing. So that's the scatter. The dots are around that a straight line increasing, an increment. There is an increment. It's clearly that that will be. So you can draw a line for this. The best line, fitted line, could be that one. So it's there will be a positive correlation. Uh, so this if you want to observe a negative relationship, so it means when y decreases, x increases. Typically, this is demand versus selling prices data reveals such a negative relationship. Maybe in our daily life, I would tell that um, when you increase the exchange rate, um, an increment in the exchange rate will have a negative effect on the stock exchange rate. So there will be a negative relationship, or maybe a better example. Let me give you from your daily life. Um, the amount of use, the amount of time you spend for your leisure life, and the less you get from your examination, um, from any lecture. So the more you spend time outside socializing, and the less you get marks. So this is a negative correlation. A positive correlation for this, the more you study and the better you get marks. So that's a positive relationship. Okay, some exercise for this one given here. Would you expect the following pairs of variable to exhibit a positive relationship, negative, or no relationship? Let's see. Age in years and weight. Yes, I would expect a positive correlation. Your weight will increase in years. When you are, think of yourself when you were a child, you were less weighted, and now you're more weighted. Of course, there will be a stabilization, and you won't gain more weight after you're 25 or 30 years of age. or it will decrease, the increment will decrease, but it is still a positive relationship. Time of day and rainfall. Um, no, there will be no relationship. The time as the time increase the rainfall, I'm not expecting the rainfall to increase or to decrease. So this is no relationship. Sales and profit, yes, definitely a very positive correlation. As the sales are increasing, your profit should increase. So two increment is a positive correlation. So this is positive. Let me write a positive correlation. Let me, okay. No correlation. Correlation and positive correlation too. What about this one? Hair color and type of car owned? No correlation, of course. Um, it doesn't mean if your hair color is blonde, you're not tend to you don't tend to own a BMW, or if your hair color is black, you don't tend to buy a Mercedes. No relationship. Okay. Um, uh, there is a data. The following data represent the education level and the annual income in $1,000 of 10 business executive days. It seems that the scan tab I did is not very successful. I'm sorry for the italic way of this data set. So um, there are 10 executives, and their years in college are given in X. That's the independent variable. Normally, we call the X as independent. This is fixed actually, but Y is dependent and is not fixed. Dependent variable. So it means X is affecting Y. Independent variables are always affecting dependent variables in practice. So if it is this guy, the first guy, is spending 4 years in college, um, his income is very high, 50. So a person spending no years in college tends to get $35,000 a year. And another guy with 5 years, spending 5 years, will get $60,000 a year. Another one is 5 years. It doesn't mean he can get the same amount of income. So it can vary. Y is very axis fixed. So that's why we call it independent, and the other one is dependent. So it's clearly that if you draw a picture of the scatter diagram of this data set, you'll see that it will be very much similar um, to that picture, that one. So it will be a positive correlation. Okay, so those are exercise. You may study yourself all this. Um, okay, let me see. Okay, you can read all this yourself. No need to spend more time for this anyway. Study all this, read all this. Please read all this data set. Um, and try to determine whether there is a positive correlation or negative correlation. Okay, now this is the official definition of the correlation coefficient from the book. In my case, it is a relationship, a measurement of relationship between two variables, one independent and the other one is dependent. So, according to the book, the book is tell that the correlation coefficient. So it is yes, it is shown with R. We use that definition R, that one. This is the correlation coefficient. Is a measure of strength of the linear relationship between two variables. Yes, it's more or less. It's my definition x and y, and it's computed. This is the computation of the correlation coefficient. So it ranges from -1 to 1. You can never get a correlation less than -1, or you can't exceed 1. And possibly you can observe a correlation 0, which is not very, it's not normal in practice. We always think that there is sometimes mostly correlation. So within this formula, x bar and y bar are the means, the average of x and y, and the summation is all over all n order pairs. I also, so according to the book, an easier expression to compute R using a calculator is this equality in 4-2. I also prefer this one. I mostly use this formula. One thing I would like to express for this formula. So this is, in my case, I write the correlation R, and I place some mostly x and y as subscript. So in my case, this formula, so I prefer to write this formula in a way that, okay, let me see. So I would have the summation here, xi. I prefer to place the indices, the subscript I from 1 to n, and this is my style. The sum of xi, I from 1 to n, and times the sum of from 1 to n y I, and that's divided by n. This is the way I prefer to write this formula, but it's not the one within the book is not incorrect. It is correct as well. Let me see. Okay. So in the first part, I place it within the square bracket, the sum of xi square minus the sum of xi squared divided by n. And the second part will be for the sum of cross product of y, yi square I from 1. You can place it yourself. The summation should always from 1 to n. So you can place it. I will place only the n here. So you will think that there will be an index starting from 1 minus the sum of yi square divided by n. So close bracket within the square root. So I'm going to increase the division. Yes. That's my formula. I mostly write this one in the book, but it is in the lecture. This one is also correct. No, nothing wrong with this description. Um, e- According to the book, if you have a large data set, the calculation will be very much difficult. So you definitely need to use a statistics software, and the book is using Minitab. It is a very famous statistic package, and you can use also Excel to calculate the correlation. Even Microsoft Excel can handle the calculation of Pearson correlation and some other statistic programs in Turkey. The most famous one is SPSS, Statistical Packages for Social Sciences, and the book is using a pure the authors are pure statistician, so Minitab is not a statistic package for social sciences. It is in general a statistic package, but since the book is um, for business statistics, maybe it is worth to use SPSS. But this book was produced 20 more than 20 years ago, a very old edition. So they prefer at that time SPSS wasn't that famous for social scientists, and he preferred the authors preferred probably Minitab, the pure statistic packages. Okay, remember the first exercise, the first example we have given right here. This example, if you consider the same example to calculate the correlation coefficient, I will expect it to be around, it's very strong correlation according to the scatter diagram, and the dots are spread around the line. So I'm expecting the Pearson correlation coefficient to be positive and very strong. Since it is strong, the relationship, I'm expecting it to be very close to 1 probably. Let's see. Okay, if you consider the same example, so you need to have the cross product multiplication x and y, and you need for the formula, within the formula you have x and y multiplication x and y, and you also have this, you need the sum of x, the sum of y, and the observation we know already, and the sum of square of x and the sum of square of y, and also you need to have the sum of x and the sum of y. Okay, let's get back to our example. So you need xy, x square, and y square. So everything, if you get all this calculation done, the sum, and the rest is easy, is like algebra. So you need to, okay, let me copy my, I'm gonna copy my formula. Let's see. Okay, okay, copy it all. Okay, gonna place it here. Let's have it here. I have some space in here. Okay, this is the formula I have written. Um, okay, let probably place it here. I have some space right here. Shorten it. Place it right here. Yes. So this is my formula. So the sum of x and y is 14. See that this is 14. The sum of x and y is 14.17. And the sum of xi, the sum of x, which is 307, you place 307 here. The sum of yi is 352, and that's right here. And this the number of observation, if you count it, 1 2 3 4 5 6 7 and 8, so that's 8 comes from there. And within the square root, I have in the first part So the book is splitting the square root into two parts. So it's wise idea. Yes, you can do that. The sum of square of xi, which is 12,315, and the sum of x, which is 307 square. You see that the square, and you divide it by the number of people, which is 8, the sum of the observation number. Okay, if you place all this, see that as I told you from the picture of this scatter diagram, we understand that this correlation is going to be a positive and very strong correlation. As I told you in the beginning, I'm expecting this correlation to be very close, very much close to 1. Okay, some summary related to the correlation coefficient. So according to the book, the following are some important things to keep in mind regarding the correlation coefficient. That's right, very much true. And this is the most significant result for the Pearson correlation. It ranges from -1 to 1. So you can never get less than -1 or greater than 0, greater than 1, I'm sorry. The larger absolute value is the stronger the relationship. Yes, that's true. R near 0 indicates that, as I told you, there is no linear relationship between x and y, and the scatter diagram typically appears to contain the shotgun effect. So it means for zero correlation, there is uncorrelation. There are x and y are uncorrelated. R equals 1 or R equals -1 implies that a perfect linear pattern exists between the two variables in the sample. That is, a single line will go through each point. So there will be no error. It means the fitted line will fit exactly. Let's see, this picture show you. So if it is, if you're expecting to be for a positive correlation, so it means you have a straight line and the dots in here, right here, no deviation. So that is going to be that way. So it will be the correlation will be +1, exactly. For negative correlation, so you should have a picture like this, and the straight line will be in the different direction, the opposite direction, and all the dot will be on the straight line, and an increment in x will have a certain decrement in the independent variables. Okay, so we have some other pictures from the book just to summarize all these related to +1, -1 correlation. The fifth one is values of R, 0, 1, or -1 are in practice, rare in practice. Yes, we don't observe such type of correlation. Sometimes this is not given in the books. I'm going to share this information with you. Sometimes we observe the correlation to be very close to 0 in practice. But this doesn't mean that there is no correlation. So you need to test it. This is because could be probably the correlation is affected by the sample size. When the sample size is very large, even if the correlation coefficient is small, and you may think that it will be significant. You can find it as significant as well. Okay, this is a very significant, very important issue related to the correlation. In many books, they try to categorize the correlation. If the correlation coefficient is between zero point 0.3 to zero point 0.5, they say, or maybe between zero point 0.1 to zero point 0.3, they say there's a weak correlation. And between zero point 0.3 and zero point 0.6, and they consider it is a mid range of um, correlation, or if the correlation coefficient is found to be greater than zero point 0.7, and they say there is a very strong linear relationship. But in fact, in my opinion, that's not true. The categorization is not that easy, because if the sample size is increasing, you can never tell that the correlation is weak or strong. It depends on the sample size, really. Okay, the sign of R tells you, the sixth one is whether the relationship between X and Y is a positive direct relationship, and negative and inverse or reverse relationship. Okay, so the sign is very significant. If it is positive, we understand that there is an indirect relationship, and for a negative or a reverse or inverse relationship, you should find a negative correlation. The seventh one, the value of R tells you nothing about the slope. Yes, because the book is study the linear regression analysis, and then they study the Pearson correlation. In my case, I would never prefer to study the linear regression analysis before you read the picture on the Pearson correlation coefficient. So this is more or less related to the last lecture. So I will have a last lecture related to linear regression analysis, and I will mention about all this in here. So in my case, I would never study the Pearson correlation after the linear regression analysis. So I'll change the order of the subject. So those pictures are very nice. I can draw all this myself. I gain also time for this drawing and presenting all this drawing to you. So this one is no correlation. So the dots are within a circle. Or you could have such dots. It's not necessarily you need to have definitely um sorry about that. Okay. So if you have this way, it doesn't mean you should observe the dots within a ball. So it looks like a square. In this case, also, there is no correlation. And the other confusing thing is, if you have a picture, a picture like this one, you will also tend to find the Pearson correlation to be zero. But in fact, the relationship is clearly that it's not really linear. It is non-linear relationship. Okay, this picture is the Pearson correlation is zero, and this one is one, because it is a straight line showing that this is a straight line. You see, that's a straight line. And this one is also a straight line, but it is an increment in x. Has you increase this one, and this is decreased. So this is y, and from time to time the decrement doesn't change. So this is why it is exactly -1, this is exactly +1, and that's exactly for 0. And this one is, you can have a straight line representing the dots. So this one is Yes, a strong correlation, which is zero point 0.9. And this one is also very strong relationship. So it is a reverse. You have a reverse line, and the Pearson correlation is calculated to be zero point minus zero point 0.8. And this one is also a positive correlation, but the dots are getting far away from the line. So this is why you're not expecting the Pearson correlation to be that high. So it's 0.5. Okay, this one is also a strong correlation, strong, positive, and this one is also strong relationship, and in both ways the correlation should be positive. Another example right here in the book, Southern Power is interested in determining the relationship between the same footage of a home and the average monthly expenditure for electricity. A random sample of 12 homes was obtained, the result of which are shown in figure 4.6. What is the value of the Pearson correlation of for this data? One thing I should definitely mention about the Pearson correlation, you definitely need to check whether uh, X and Y actually, yes, X should be also normal. They should have a Gaussian distribution. So you need to check whether the if your data set is very small data set for this one, just to give an example to clarify the idea how you calculate the Pearson correlation we study mostly in many books, you observe that the sample size is too small, just to for easy calculation, easy illustration. Okay, so this is the example. We don't check according to the book. The book doesn't change whether the data set has a normal distribution. To do that, you definitely need a statistics software like SPSS also. So you have two variable, one x and the other one, this is independent, and that's dependent variable. Okay, let me read the example. Southern Power is interesting in determining the relationship between square footage of a home and the average monthly expenditure for electricity. A random of 12 homes was obtained, the result of which are shown in 4.6 figure. And what is the value of R for this data? Okay, if you draw a picture of the diagram, scatter diagram, and you'll see that it's clearly um, you have a linear relationship. I'm expecting to be very much high, which is very high, 0.688. Okay, to do that, what do, you perform the same table calculation here, the sum of x I y I, which is here, the sum of x 269, and the sum of y 330, 23.6, and so on. You produce the same table as we did in the first example. We had this table. Let me see. Remind you this. Okay. Okay, right here, somewhere here. Um, okay, I can't find it anyway. Let's get back to our study. Okay, the Pearson correlation. Um, not this one, sorry. Okay, this one. Um, you prepare the same table as you did in the previous example, and it makes the calculation easy. To get this value, you get it easily. Okay, there is another data set you can study yourself. Bollywood Brockwood Homes is a major developer of suburban homes. The president of the company wants to determine what relationship, if any, exists between the number of times and then their model homes were shown to prospective buyers and the number of homes sold. The data from 50 months were gathered and shown in table 4.3, and the question is, does it appear that there is a positive relationship between those two variables? Okay, the solution, it is too simple. Everything you substitute all this value within the formula of the Pearson correlation. This is the scatter diagram of the number of houses against the number of houses sold. So in my case, since the distribution is random, so there is no relationship. I can't have a straight line representing this. Well, this is like a circle, more or less a circle. Okay, so it seems to be large value. As I told you, this information does not exist in the book. Since the sample size is small, you always tend to find the Pearson correlation to be large enough, like 0.2, 0.3 something. In our case, you can consider it is to be significant. Significant is a popular word in the world of statistics. We mostly use it. Um, okay, if the difference is important, we call it significant. So this is a standard term for statistician we always use. Okay. Um, oh, the question is, according to the book, is where would you classify R? Is this value of large enough to say that there is a linear pattern to this data? In my case, no, I can't. I definitely need to test these statistics, and if I find it significant, and I will conclude that there is a positive, strong or relationship at least. Um, yeah, this is a good table. That's what I mentioned about. You can see it in many books. So this is very useful. See that um, for 5% of linear relationship, if you have a amount of people, so you tend to get the Pearson correlation to be very large. But in fact, even if it is 0.532, which is equivalent to this one, actually, is because this is use more than around 14 observations, and this one is using only 5, which is in fact uh, you sh- you must be very careful. Look at that. This is a strong relationship. 0.374. The sample size is 100. But I will consider this is to be very significant. I wouldn't treat this to be a weak relationship. Okay? So this is, um, in fact, this is the range given for a strong relationship and a reverse relationship, and this is a strong um, positive relationship. But in my case, I wouldn't like to have such range because there is no standard definition for this very significant linear relationship and very significant to linear relationship. Okay, you can perform all this reading yourself. I will skip all this. You can read it yourself, understand. Um, you can draw some conclusions from table 4.4, and that's the conclusion. As I told you, one of the most significant conclusion for this table, if you have less observations, very few observations, you tend to find the Pearson correlation to be large, which is in fact can't be, it shouldn't be a correlation. Okay, read all this yourself and draw the conclusion from 4.4, and let's get back to another example. So this is x and y, so definitely you need to have x and y cross product multiplication, and you need to have xi square. Let's delete the index here, just xi. Okay, and you also have yi square, and what else? And you also need to have the sum of xi and the sum of yi. Okay, so all these are calculated here, so you can check yourself whether this is true or not. Please do check whether all this calculation is perfectly fine. Okay, yes, that's the sum of cross product xi yi, and this is the sum of x, and that's the sum of yi. Okay, those exercises are worth to read. The first one is, are the following values of R for sample size n significant according to table 4.4, testing that there's no linear relationship. It's clearly, as I told you, if the sample size is too small, um, even if the correlation coefficient is very close to zero, we didn't consider that there is no correlation. We will tell that in conclusion. We'll tell that x is affecting y, and this is clearly observed from this calculation. And this one is the sample size is very fairly large, and the correlation is very small. So I'm sure I will tend to reject the null hypothesis having no correlation. So it will be accepted. You won't reject the until um, for you won't reject the null hypothesis for R 0.175 for large sample sizes. Okay, read all this exercise yourself. Consider all these exercises, and um, if you find something hard to study all this, and you can contact with me for this, definitely for the correlation analysis. And this, it seems that the end of the lecture actually, and we will study next lecture another correlation analysis when you can't apply the Pearson correlation, and if you suspect the data set has non-Gaussian distribution, and we use an alternative non-parametric correlation coefficient, which is called the Spearman rank correlation. And we will also test how you we will definitely test the correlation you obtain, whether it is significant or not in the next lecture. So up to now, so far, what I teach today, this is the end of the lecture, and I hope you can understand easily from the link supplying each week from, and you can easily access to the internet to view my videos, my lectures. And another thing about the examination, I was supposed to upload my examination question, my examination homework today. I'm late, just a single or 2 days later. I will definitely upload my exercises. You will study yourself at home by yourself. I haven't prepared it yet, but tomorrow or the day after, you will have the examination paper anyway. I will also, beside the video, I will also try to have my lecture notes as a PDF file and send you to Lapses and to the group we created within WhatsApp, and to the system for the distant education. And you will see, it will appear on my lecture weeks, the related weeks, which is a 12th week. So I guess this is the end today, and stay safe and have a nice day. Stay safe and good day. Bye. Bye, everyone.